Okay, so we're looking at cubic unit cells. We saw 3 examples, and part 1 goes through those 3 and looks at coordination number, which is how many other atoms are connected to each other, and how many atoms are in one unit cell. So we expect that cell content to be the lowest for the simple cubic unit cell because its packing efficiency is lowest, right? And so all we have here are 8 atoms on each corner, which each atom contributes 1/8. So 8 times 1/8 equals 1. So the unit cell content is 1 atom per unit cell. And it's a little more difficult to see how many atoms are connected to each other here. And if we're looking at this atom here, we can see there's one to the right, one above, and one in the back. But you have to remember that we have also cells connected to each other. So looking at that particular atom, we have actually 6. So the coordination number is 6, right? So there's another one here, and then there's another one here, and another one here. So that's what we're looking at for coordination number. Simple cubic unit cell coordination number 6. And the atom content is 1. Moving on to the body-centered cubic unit cell. So now we have a higher packing efficiency. We are expecting to have more atoms in the cell, and we do. We have 2 because we still have the 8 on the corner, which contributes 1, and then we are adding the one that's in the center, completely embedded, completely 100% part of that cell, which you can tell the golden sphere in the center is completely embedded. And so this the coordination number is actually easier to see here than it is here, because you can tell that the one in the center is connected to all 8 atoms on the corner. So coordination number 8, and unit cell content is 2, the one in the center, plus the 1 for the 8 corners. Looking at the face-centered cubic unit cell, you can of course look at the answer. It goes up. Your packing efficiency is the highest there, so we expect that. We have, instead of an atom in the center, we now have 6 atoms on the face, and each atom on a face, we have 6 faces here, contributes a half. That's a total of 3, and then the ones on the corner is 1, and so we have a total cell content of 4 atoms here. All right, and the coordination number, of course, is 12, and it's a little bit more difficult to see where the 12 are, but I'm having a little bit of a hard time myself, so let's just stick with 12. Right? We'd have to rotate. I'd have to look at a physical 3D model. All right, so let's take a look at. We can do this without guidance now. We can look at a random unit cell. This is cesium chloride, and determine the content. Of course, now we have 2 different atoms. We have cesium and chloride atoms, whereas the ones we looked at all had the same type of atom. They're either aluminum or platinum, or usually a single metal that will pack efficiently like that. So this is pretty easy. It's a body-centered unit cell, and the one in the center is, of course, a cesium, and then we have 8 on the corner, and so 8 times 1/8 is also 1. So these are in a 1-to-1 ratio. There's 1 cesium atom or ion and 1 chloride ion per unit cell, and it makes sense that they are in a 1-to-1 ratio because we know that cesium chloride has the formula of CsCl. All right. Jumping to something drastically more complicated. Okay, this is a cubic unit cell, but it is sodium chloride, which is in a 1-to-1 ratio. And so the new thing here is we have atoms on the corner, right? We know that we have sodium ions, not the corner, but the edge. The chloride ions are on the edge. So this is something new that we haven't seen. But we know we have sodium ions on the 8 corners. So we have 8 times 1/8, which is 1 sodium ion on the corner. And then we also have sodium ions on each face. So all 6 faces have a sodium ion. So 6 times 1/2, which is 3 sodium ions. And so we have a total of 4 sodium ions in the unit cell. And then the chlorides, we have 1 in the center. All right. So there's 1 chloride in the center. And then we have the edge. Okay, so these are here all on the edge. And so if you look at this as layers, right? So we have 1 layer here, and the second layer here, and a third layer there. Each layer has 4 of those, right? So 1, 2, 3, 4, and then 8, and then 12. So there are actually 12 on the edge. So 12 atoms on the edge. And so you have to imagine the percent that this is part of, and it's actually 1/4, which then gives you 3 chloride atoms. You add them up, you have 4 chloride atoms. The total unit cell content is 4 chlorides and 4 sodium atoms or ions. And just in case you don't see it, right, that this is 1/4, just imagine how many cubes it would take to completely embed that, right? So if you have to have 4 cubes that are connected to get the corner completely embedded. All right, so moving on to the next factor. So we want to know packing efficiency. We've done the coordination number, and we have done cell content. Now we're going to look at the relationship between length and radius of a unit cell. The simple cubic unit cell is actually pretty easy to determine, right? Because they touch each other here. So we have 1 length is going to be equal to 2r. So there's no gaps like there are along the length, and all of the length here, of course, are the same. So that's basically it. So the cell length is equal to 2r. Gets a little bit more complicated for the body-centered unit cell. You've got a little bit of a gap here, so L is not easily expressed in terms of R. We have to use a little bit of math here. And so if we look at a section of this cube that is completely connected by atoms, it would be the diagonal through the entire group, from not on one of the faces, but from one of the opposite corners here, right? So we can see that there's half of a purple one, a full, and again, it's just color coding, so you can tell them apart, but they're all the same atom. They have the same radius. Otherwise, this math does not compute. So here, the distance C is actually equal to 4r. Okay, and so we use Pythagorean theorem, where we can argue that C squared, because you have a 90 degree. It doesn't look it, but it's a 90 degree angle here. So we can say that C squared equals B squared plus L squared, and if we want to express L in terms of R, you want to get rid of C and B, we can start doing that by saying, okay, so 4R squared equals B squared plus L squared. Now we need to find a relationship between L and B, and that one is very easy here, because we have another triangle here with a 90 degree angle. So this is L and this is L. So we also know that B squared equals L squared plus L squared, and if we substitute that, we get 4R squared plus L squared for this, plus L squared, which is equal to 3L squared. If we put everything, if we isolate L now, so I'm going to divide by 3 on both sides. I'm going to put L on the left, so I'm going to say L is going to equal to, I still have L squared, 4R squared divided by 3. And now if I take the square root of both sides to get to have L by itself, I then get L equal to 4R divided by the square root of 3. And so this is the relationship of L to the radius.